Hey, welcome back to Integral Calculus Part 2. Do you remember what Part 1 was about? It's something to do with this area under the velocity time graph, and how that if we found the integral from t1 to t2, it would give us the total displacement or total distance travelled. Okay, because the velocity time graph is a graph of s-t against t. And what we wanted to do was to investigate coming back and finding under the derivative graph what the value of that function s was. Okay, and we wanted to find the distance travelled as a result. And when we went on this journey and said, could we find an estimate for that area? We're talking about upper and lower sums here, and more rectangles drawn. Okay, and we came to this result, that the actual area function was somewhere between the values of the limit as n tends to infinity, more and more rectangles of the lower area and the upper area, and that if you made a mass of those rectangles, made them just one whole if you like, integrated them all if you like, then these two are the same. In other words, the upper and lower limits, the upper and lower areas have the same limit. So that meant the area, the actual area we want, would be jammed between these. If only we could find what that limit was. And this is what we're trying to do down here. Find the limit as n tends to infinity of the sum of an infinite number of rectangles of width, delta x, and height of the function, of course. Okay, and can we do that? No, we can't find an infinite number. Okay, infinity is abstract quantity, but can we find what it tends to? And that was our journey. And this was the symbol for finding the limit. So this is representing the sum. It's like an S stretched out over a certain interval. We want an infinite number of rectangles drawn there, and this is reflective of the fact that it's the height given by the function value. This is reflecting the delta x over here. And the whole thing, this represents the sum of an infinite number of rectangles. And we still haven't actually been able to, at this stage, be able to find that. We can only estimate it by drawing more and more rectangles. Okay? But then we investigated, looking at limits and calculus, we found a very, very important result. And that was the area giving function has as its derivative the function that we've just drawn. The area under the function that we've just drawn has as its derivative that function itself. Interesting, very, very interesting result. So you go back to perhaps first presentation and have a look at that. So what did we end up with then? We said if you wanted to find the sum of the infinite number of rectangles and come back and finally find the answer back up here, you actually had to find f. Now what is f? Well, f is the function which is going to give you the area. So f dash x is our original function. So what do we have to do to find the sum of the infinite number of rectangles under the function? We have to find the function whose derivative is this. So we've got to come backwards. We've got to treat that as a derivative and anti-derivative it, if you like, and then evaluate that function across the interval, and that will give us the sum of an infinite number of rectangles. An interesting result, isn't it? That the function we needed is that function whose derivative is the function whose graph we have drawn. So, very, very important result. The area given function, its derivative is the function itself. We've got to go backwards, therefore, don't we? We've got to undifferentiate or anti-differentiate. Let's have a look at it down here now. So we'll just come up here a little bit. Oops, hang on. There, I think we want to go. All right, okay. So if we take a function and find its derivative, differentiation, then we could represent it with one of those two symbols. What are we doing? Let's go to Huddy's trichotomy here. Here we go. The derivative means what? It means the slope of the tangent, or it means the instantaneous rate of change. We'll go around the circle, instantaneous rate of change of the function. And all of those are synonymous, if you like. So when you see derivative, you think of those three things. Around and round we go. Now what we want to do now is do the undo that operation, okay, because we have found that to find this sum of an infinite number of rectangles drawn under the graph, that's this representation here, we need this function. And this function has as its derivative the original function we drew. Okay, so we've got to take our original function as if it's a derivative and undo it and go back to our function. And we're going to call that process integration. Why? Because the answer to that process is going to enable us to do this infinite sum of rectangles there. Okay, which is the fundamental theorem. This is the fundamental theorem of calculus. Okay, so to do that, we're going to do that. And when we do that infinite sum, we make a whole mass, don't we, under the curve, making a whole integrate. A whole. So there's a fair bit of meaning in all these symbols there. And then we get back to the original function of whose derivative we have. So we want to go backwards now to fulfill our need to do this thing here. All right, let's try and go backwards, anti-differentiation or integration. So here it is here, the integration formula. We're going backwards. Well, first of all, if we had the derivative was 1, what would the original function have been? Well, remember the rule? If you have x to the n, the derivative is nx n minus 1. So if you have 1 is x to the naught, what are we going to do? We're going to have to reverse this procedure. That goes that way. We've got to go back again. We've got to increase the power by 1, divide by the new power, if you like. Let's look at the rule here they've got. This is from Pearson's now. X to the m plus 1 is m plus 1 x to the n. Or we can write it like this. So what are we going to do? N is not equal to 1. Otherwise, you just get this case up here. What are you going to do in coming backwards? Using the sign for anti-differentiation or integration, then it's increase the power by 1, divide by the new power. That's reversing that rule. Okay, we're reversing the rule. If you like, anti-differentiation. Well, we shouldn't put it across there. This is anti-differentiation, isn't it? You have to get your head around this carefully because it's the opposite to each rule now. Okay. Now, that's interesting, but what's this? What's this? C is the constant of integration. What's that doing there? Can you see why we need it? Well, let's check it out now. If we said our derivative was x squared and we wanted to reverse that, put the integral sign coming backwards, that would be x cubed on 3 plus c. Why plus c? Let's check it. Let's check now the derivative of x cubed on 3. Does it work? Plus c. So let's do this one. It's the third. The derivative of x cubed is 3x squared. And the derivative of c is 0. Oh yes, that gives us x squared. Hang on, what's the c? Well, let's say it was 2, a constant of 2. Can you see what's going to happen? That constant contributes nothing to the derivative. So there's actually a whole family of functions, all differing by a constant, that produce that same derivative. Okay, there's a family of functions. Do not omit c. It's an important concept. You will lose a mark in any test or exam if you do it, if you lose the c. Because the idea is, it is not just one function whose derivative is this. We're coming backwards. That's the core function. But all functions that only have c attached to that basic function will have the same derivative. Look at it down here. The derivative never contributes anything. The constant, never contributes anything to the derivative. So please, when you're doing anti-differentiation, or we're going to call it integration from now on, coming backwards, then you must have that plus c in there. So the derivative of sine x is cos x. So if you want to reverse cos x, you'll get sine x back, plus c. Derivative of cos x is minus sine x. So look out. and we've changed the symbols here, it can be anything. You can talk about the variable x or v or what t because of motion problems and so on. So here, if we want to integrate the sine, just look out, it's minus cos. Okay, because of this negative over here. So if you're integrating sine, it's minus cos. And we'll check it backwards because the derivative of cos is minus sine. With that minus would give us the plus there. Okay, so you have to watch those things to go backwards there. All right, so just check the next one. Derivative of tan is sec squared. So the integral of sec squared is tan plus c all the time. Derivative of e to the v is itself. The integral of e to the v is e to the v plus a constant. Now this is an interesting one. Derivative of ln mod x, or absolute value of x, because ln cannot be found. X must be greater than 0 for ln to be defined. So your derivative of ln mod x is 1 on x, and therefore the integral of 1 on x is ln mod x plus c. Or you can put x must be greater than 0. Okay, so what's this one? It's rather easy to remember, because if you try to do it with as x to the neg 1, when you do it with the x to the n rule, you'll get neg 1 plus 1 over neg 1 increase in power by 1 divided by new power over 0. So this doesn't work. So you can't actually go wrong with the integral of 1 on x, because you would increase power by 1 divided by new power, which wouldn't work. So you know, oh, I better remember that. That's ln. Okay, so if you try to integrate 1 on x in the power rule, it won't work. So relatively easy to remember. But look out which way you're going. It gets hard in tests where you've got both differentiation and integration problems to remember which way you're going. So just check that. All right, let's have a look at some problems now. These come from Hayes and Harris. We're going to find the integral of that with respect to x. Notice that this tells you what the variable is, okay, with respect to, well, the original widths of those infinite number of rectangles, if you like. So I could rewrite the problem as t cubed take 2t squared plus 5. But if I'm telling people to do the same thing, the variable name is t here. Okay, so let's just get those symbols right. So what about something like this? X cubed take 2x squared plus 5t plus 6. Now, can you see our problem? What variable are we talking about? This one or this one, x or t? So if I did this and put with respect to x, this would be deemed to be a constant. Okay? Because that's not named as the variable. So this down the end is said with respect to. Okay? With respect to. So naming the width of the rectangles that you would have originally drawn in terms of what is along the x-axis with respect to. Okay. So a little bit of notation here. So this is okay. Let's do it. Let's increase the power by 1 divided by new power. Neg 2, increase the power by 1 divided by new power. And then 5, derivative of a constant is 0, but we're doing the opposite. It is 5x plus c. Very, very important. Always remembering there's a whole family of functions which, when differentiated, will give the original function. Let's look at this one. Oh, nasty. We're going to have to change that to a power, and this one to a power, and naming the variable with respect to x, and so increasing the power by 1. Remember, neg 3 plus 1 is neg 2 divided by a new power, and a half plus 1 is 3 over 2 divided by 3 over 2. So here, putting x to the neg 2 down the bottom line. Okay, and 3 over 2 inverting and multiplying. So just keep your wits about you here. This is important to keep in mind, that the rule now for integration, increase the power by 1, divide by the new power, that idea. That's the integral. All right, let's go on and have a look at these couple here. So integral of 2 sine x take cos x with respect to x, just naming the variable on the independent axis, naming the variable, okay, that you're moving along. I like students to remember that this is reminiscent of the delta x in the limit formula, fxi, sum from I equals 1 to n. We want the limit of that. So that's naming the width of the rectangles along the x-axis or the t-axis. It's telling you which is the variable name there. So let's have this. The integral of sine is minus cos. You know how I remember this in teaching? I think of sine is friendly, okay, on differentiation, and cosine is not. Why friendly? Because you don't have a negative in it, whereas derivative of cos is minus sine. And of course on integration it's the opposite. The integral of sine is unfriendly, because you've got to remember to put in minus cos. The integral of cos is friendly. There's no negative in there. Okay, so that's one way to go. And so let's do the cos here. You've got neg and then, or subtract, and then the integral of cos is just sine, and then we can write in a slightly simpler form there. Okay, what about this one? Bring in 2 on x. So it's neg 2 ln mod x plus 3 by integral of e to the x's itself, as it is with differentiation, plus c. Just check our c's every time. It will be penalised every time you make that mistake in a paper, because it is a concept. You must know that the differentiation of functions which only differ by a constant gives the same derivative, are the same. Okay, so let's have a look at this one. Now this is a function done to a function. So we haven't actually come to a point yet where we can reverse that functional function or composite function situation, and in this one anyway you would have to expand it. Okay, so square the first one, 9x squared, twice the product is 12. If we just check that now, 3x times 2x, 2 on x times 2. Right, 2ab, remember, a plus b all squared, first one squared plus twice the product plus the second one squared. So there we have it, 3 by 2 by 2 is 12. Should be able to do that straight up, otherwise you'll have to FOIL it. Bit slow though. And this would then be 4 on x squared. So converting it all to powers of x, and then doing the integration, we remove the integration sign here, and 9x cubed on 3, 12x, and then increasing power by 1. Neg 2 plus 1 is neg 1 divided by the new power. And so there we have our final function. Don't forget the c. As soon as you do the integration, you must have the constant there. Okay, over here, same thing. What we're going to do is say x squared take 2 all divided by root x means x squared on root x take 2 on root x. So this is a single power. 2 minus a power of a half, root x is a half, is x to the 3 on 2. And x, root x in the bottom line is x to the neg a half. And now we can do it. Increase the power by 1, add 1, divide by the new power. Increase the power by 1, neg a half plus 1 is a half divided by new power. And then we invert these. Now you're dividing by a fraction, you invert and multiply. And then as soon as we do it, add c. As soon as you do that anti-differentiation process, you must have a constant in there. Alright, let's come down and give you a go now. So you have to do most of these, I think, to get the skills up. So there's question 1 and 2. Usual idea. Pause the presentation, have a go, and I'll scroll down to the answers in a minute. Okay, question 3. A bit more there. And let's go on to question 4. 5, 6 and 7. Okay. Some mixed bag there. Just remember, here a different setting out. The derivative is that. So you will do the antiderivative or integrate that. Just a little note here. If you want the integral of a derivative with respect to x, that gives the function back again, doesn't it? So what you need to do, if you have the derivative, you need to integrate that. Okay, just a slightly different way of setting up the question, telling you you've got a derivative, so to get the function back again you'll have to integrate. Alright, and here again the same thing. I hope you have seen from the presentation that if I give you the derivative, the process of getting the function back again is to integrate that from the original expressions we talked about and the roots of the fundamental theorem of calculus. That's the idea, that you will get the function back again. Alright, have a go. Here come the solutions. Okay, 1, 2 and 3. And 4, 5, 6 and 7. Okay, let's go on to one other type in this presentation. And there's a couple of others still in integration to see how it all evolves and how we can use it in actual fact. So if we're given the derivative like that, and we're also given a function value, f of 0 is 2, what could we do? Let's have a look. Here's a derivative, so we'll get the function back by integrating it. We'll do each power, x cubed on 4, increase the power by 1 divided by a new power. 3 would be 3x. You can think of that as what would happen to that when you differentiate 3x. You just get the 3, so it's x plus c. Now, but we're given that the function value is 2 when x is 0. So let's put 0 in the function. Here, here and here. And when you do that, the function value is 2. So plus c would be 2. So we've actually found the c value. So if we're given another condition on the function, we can use that to what we call evaluate the constant of integration. Evaluate the constant of integration. And therefore the final function is known to us, including the constant. So this will come up pretty importantly in applied problems later on when we use this for something other than an exercise, but a bit of a useful application coming up. There's several of them. So if we're given this derivative and we're given a condition, in this case it's the value of the function when x is 0, let's try the process. Let's integrate it with respect to x. Setting out's important. So here it's 2 times, now the integral of sine x, that's not friendly on integration. It's minus cos x, minus, now increase the power by 1. A half plus 1 is 3 over 2, divide by the new power, plus c. Therefore, the function in simpler form is neg 2 cos 3x, dividing by 3 over 2, invert and multiply. Okay, now we can sub in. F of 0 is 4. So when x is 0, we'll put it in all the x holes here. Okay, that plus c is 4. And so here, so c is 6. I have left that out. Cos of 0 is 1. So this means this is neg 2, take 0 plus c is 4. So neg 2 plus c is 4. C adding the 2 is 6. They've taken that for granted that you can see that. I'm just making sure that you can. And then you put the whole function back together again with an actual value of c. So there is a unique function. Okay, this is unique now because we're given a particular initial condition there, or condition for the value of the variable being 0. So we can actually get a unique member of that family. Okay, let's go down and have a look at some more. Have a look at this one. We've got the second derivative and the first derivative. So we're going to have to come backwards through stages, and the function value here. So let's take the second derivative, go back to the first derivative by increasing the power by 1, dividing by a new power, take 4x plus c. Now we can use this information down here to actually evaluate that c. Okay, so this says when x is 0 in these holes, the answer is neg 1. So put the x is 0 in there, plus c is neg 1. And so we've been able to get a unique value, or unique expression for the derivative. There it is there. Well, now we'll do it again. We want to integrate that. So increase the power by 1, divide by the new power, these cases, and the integral of neg 1 is neg x, and plus d. Now we must use a different constant here, because we don't know that the unique member we are trying to hunt down has the same constant. So must use a different constant of integration on repeated integration. Okay, so now we will go and hunt for that. So there's our function. Go back up here, look up here, and we say when x is 1, the function is 4. So in the x holes here, here, and here, we're going to put 1 plus d is 4, and then solving this, we've got d is 6 again. We can go through that. So we have a unique final function. So there could be in a problem more than one stage of integration if you want to come back from the second derivative. Okay, are you ready? Let's go down and try some problems where we can evaluate the constant of integration and get a unique function. Okay, find f of x given the derivative. And we're given a condition on it. So you can find an expression with c in it for the function, and then substitute in x is 0 and the function value 3 and evaluate c. Okay, have a go. Do most of these, I think, to keep your skill level up. And now I'll show you the answers. So pause it, have a go, and I'll show you the answers now. Okay, so I hope you're building up some skills, because we need those. We're going to go further with rules of integration, and then we're going to look at some applications, some really useful stuff that we can do with it. Anyway, I'll catch you then. Cheers for now.